Hi everyone, welcome back. Now I'm going to continue with the other technique. Let's remember where we are. I was talking about image segmentation. Fundamental techniques are finished. We are trying to apply graph theory to image segmentation. One particular example was given. It was in a method called RSSD, which is bottom to up technique. We are merging pixels to find the semantic objects. Now I'm going to show another technique, which is a very famous one. It is dated back to 2007. After 10 years, the algorithm that I'm going to show you right now is one of the most influential papers, selected as one of the most influential paper called Normalized Cuts. I have to give some definitions basically first of all, then I'm gonna continue to how we're gonna make segmentation through graphs. Okay, now first of all I'm gonna define something called adjacency similarity matrix. First of all, I'm talking about again pixels or some regions are being the nodes of the graph, the neighboring points, neighboring nodes, neighboring pixels will have an edges. Now we are having the edge information, the relation between neighboring pixels are this time stored to a W matrix. At this time, by the way, we are not taking differences, but we are not looking to the how similar they are. We are looking to the how similar they are rather than how different they are. Therefore, a number here which is large, which is typically showing some similarity between two pixels, two regions. If it is small, less similarity. Therefore, we basically what we do is e to the power minus distance divided by any normalization sigma over there. Okay, the degree of the vertex is nothing but the sum of the similarities between all its neighbors. Therefore, let's maybe go over this example here. This is a very simple 2D example. These are like 4x4 pixels here. These are our nodes. Let's assume at this point, although not necessarily, for example, 6 node is connected only to 5, 7, 10. In fact, in this realization, I can connect everything to everyone, but let's assume 4 connected right now. Now, what I'm doing is the similarity between 6 pixel and the 2 pixel is written to a matrix like this, and in this matrix, this Wij not position, in other words, to 2 and 6 or 6 and 2, okay, this point and that point, we are simply writing whatever the information here is, like 5, we write it here as 5. If it is like 0 to 1, we should write, for example, 0.7 to here and here, indicating that 6 pixel and 2 pixel are similar with 0.6. The degree vertex is nothing but this 2 pixels, all its neighbors, we basically sum its similarities to its neighbors. Okay, we call it degree matrix. This degree matrix is obtained by putting the di to the diagonal entries, just like here. Assume, by the way, this adjacency matrix in the diagonal we put zeros. Otherwise, nothing but similarity between the pixels. Here, this D matrix, diagonal matrix, is the degree matrix, is something diagonal. We just sum nothing but Wij and write it to the diagonal. Everything in other than this is equal to 0. Okay. Therefore, this is our diagonal matrix. Now, if we subtract D from W, okay, D minus W, let's call it graph Laplacian matrix. Let's right now don't consider why do we call it Laplacian. Later it will be more clear. But we basically subtract these two things from each other and we call them unnormalized. There will be a normalized version as well. Graph Laplacian matrix. We have vertex set. This is a subset of all the vertices. Let's assume the segmentation pixels 6, 10, and 11 6, 10, and 11 over 3 pixels belonging to object A. The others 1, 2, 3, 4, 5, 7, 8, they are belonging to B. Therefore, 6, 10, and 11 are vertex subset A. Okay, and the volume of these things, 6, 10, and 11, the volume is nothing but the 6th one here, 10th one, and the 11th one, the blue things right here, this one for 6, this one for 10, this one for 11. The volume A means all the nodes in segment A and the sum of the similarities between its neighbors are stored into volume A. Okay. Now the indicator function is like this time a vector. Okay, this time a vector. Just like, for example, if you're interested with 6, 10, 11, you write zeros here. Okay, when it is 6, 10, and 11, you put a 1. Otherwise, it's 0, you put a 1. Okay, and this is your indicator. Please note that if you multiply, for example, your indicator with D, okay, if you just multiply your indicator with D, this is diagonal, please note. This multiplication will multiply only 6, 10, and 11 with ones, which will nothing but the sum of them, and the remaining ones will be 0. Therefore, this indicator of A multiplied with D is giving you volume of A. Okay, now the similarity between nodes are represented by a weighted adjacency affinity matrix. Similar nodes have higher entries. Therefore, let's give an arbitrary example. Here they show its similarity. There are high numbers here, high number, 2 low numbers there. Therefore, if you would like to look into this graph, you would like to cluster them, segment them. This is maybe one object, the other one is another object or a region, okay? And these regions are basically giving us 2 things, okay? Now this adjacency affinity matrix is shown in this way, okay? Therefore, let's assume we are numbering like 1, 2, 3, 4 here, okay? And these things are 1, 2, 3, 4. These are 1, 2, 3, 4, 5, 6, 7, 8. The other ones are here. As you can see, bright pixels here for this visualization. This is nothing but a visualization of a matrix, just for your eyes. Showing that these numbers connected to each other giving you high values, brighter spots, and these are also brighter spots, but these things are very low and there is no other connection between them. They are black, okay? If 1, 2, 3, 4 here, 5, 6, 7, 9 here, that will be a typical adjacency affinity matrix. Okay, our aim is for segmentation, for clustering, is dividing this graph into subgraphs with strong links inside, okay? Therefore, obviously, this is one strong link inside, one other strong. These are weak links. I want to cut them by somehow. I don't know how to do it right now, but I'm going to try to do it here. Let's go back to, again, how do we define an affinity in terms of intensities? Just intensity of x and y, you subtract them, e to the minus divided by a sigma I square. You will have, for example, an intensity-based affinity matrix fill. Here is a toy example, no intensities, 40 numbers here, only xy locations. They are numbered by luck, 1, 2, 3, 4, 10, 11, 12, 19, 20, 20. It goes on like this, and you have beautiful these matrices. The difference between these 3 matrices are nothing but the sigmas here, okay? Based on these sigmas, we will have different numbers here, because this sigma being very small, everything will be quickly becoming very small number if it is something large here. Therefore, I have to be considering this sigma while I am filling my affinity matrix. I don't know how to find the scale, but scale is an important parameter while you are defining distances. Therefore, these are obviously different things. There are 4 clusters here, 4 submatrices by luckily numbering them correctly. Typical numbering is 1, 2, 3, 4, 5, 6, 7. Therefore, we don't know how to number them. But we realize that there are some submatrices, and those submatrices are more visible if we find a good scale. Okay, now let's look at the graph theoretical clustering. Now the idea is, let's find a vector f. That will give us an association. This f is like this f here, okay? This is the f I'm talking about. Therefore, this is like an f here. This f matrix is a non-zero entry is giving us the membership. For cluster A, for segment A, there will be ones, otherwise zeros, for example. But I have to give the ones in such a way that the ones inside this cluster should have strong similarity between, okay? If I go back to here, maybe this should be 0.9, this should be 0.8, very like maximum 1. These are small numbers, 0.01, 0.02, these are 0.01, okay? Therefore, we are talking about strong similarity inside. Between here, maybe, again, 0.9. Now, the aim here is this. If I multiply this W matrix from left and from right with this F, okay? F indicating the nothing but the indicator function, showing where the nodes of group A, cluster A, segment A are. If I just multiply this, please note, this multiplication, this vector, multiply with this one, for this example, certainly will give us, okay, will give us strong large numbers, with large numbers, okay, where these 0.9s are calculated. Therefore, multiplying from left and right with such a F matrix, where the entries show our membership of one cluster, if we maximize it, we are maximizing nothing but the volume inside these things, okay? Therefore, this will be nothing but multiplying distance from left and right. If Wij, like between 10 and 6, this one and from 6, and the other one from 10, between 6 and 10, you will have 0.9 included here, okay? This will be including 0.9. Similarly, 10 and 11, this is with 10, which is with 11, 1. This multiplication will give us, again, a very high number. For all the others, please note, if this one and that one is 0, one of them is 0, that Wij will not be included. I am just including the ones, hopefully, with high similarity values over there. Now, therefore, this multiplication maximizes in case all three terms are non-zero. Wij should be non-zero, the Fi should be non-zero, Fj should be non-zero, okay? In this example, please note, I have a similar case. If I put here at 6, 10, 11 ones, all the zeros, hopefully all those high numbers will be collected from that. Now, obviously, a very trivial thing for maximization of this thing, you will make f going to infinity, okay? F will go to infinity, and therefore, if f will go to infinity, we will see that we will have nothing but our this thing going to infinity for f, and the result is maximized. I have to put an extra constraint saying that the energy of this, the values you can insert into this vector is limited. You cannot freely write any number so that you obtain a good solution, a non-trivial solution. Okay? Now, if you look at my background notes in the optic class, you will see that such a technique, maximization of this with this constraint, linear constraint, equality constraint, is obtained through a method of Lagrange multiplier, okay? And we simply add with a multiplicative factor lambda here, just writing as a 1 minus the constraint here, like a 0 here, okay? To satisfy, we have to make it 0. Therefore, either this one will be 0 or that one will be 0, and you are maximizing this thing, okay? Therefore, solution is taking the derivative. Please note, we did before, taking the derivative of this thing with respect to f and equate to 0 will give us nothing but our the famous eigenvalue solution. Therefore, we obtain a matrix times an unknown f is equal to lambda times f. This is the f satisfying. This is nothing but the eigenvectors of w, and lambda is the eigenvalues of it. Therefore, since if you insert this wf, just please note, since we are trying to maximize this, oh, sorry, since we are trying to maximize this, okay, this is equal to lambda f. Therefore, f transpose f lambda is scalar. That is eigenvector equal to 1. Therefore, the maximization thing is lambda. Therefore, I have to select the eigenvector of w with the largest eigenvalue. If I do so, I'm going to obtain a vector where the entries will give me the positions. They will indicate me the memberships of nothing but my group A, one of the most strong similar segment cluster in my problem. Okay, now if you look at here, the previous problem here, now I'm gonna say these are again 40 points. This is the affinity matrix. Now if you go and find the eigenvector corresponding to the largest eigenvalues, you obtain this one. 40 points creates the similarity matrix 40 by 40. This is an eigenvector 0 to 40 or 0 to 39, total 40 numbers here. Please look at here, the eigenvector values are shown. 30 of them are very small. 31, 32 going to the 40th one will be these guys, okay? I think this is these guys. They have very large values. Now, the system says this. I gave you an indicator function consisting of very small, almost 0 numbers, and some high numbers. These positions, 31, 32, indicating in this graph were most similar in terms of distance, Euclidean distance, nothing about intensities, just distance between them. Most similar cluster that we are trying to find. Okay, therefore, if you look at here, we realize that this eigenvector, the entries thresholded. Threshold, just removing these small ones from those large ones. If you threshold it, you obtain nothing but the positions of your entries of the indices 31, 32, 33, all these nodes, saying that these are belonging to one group here. Therefore, this simple technique, very simple technique, an affinity matrix, an eigenanalysis, the eigenvector corresponding to the largest eigenvalue, is simply giving us a solution for the nodes, the pixels, whatever, here in this toy example, for the nodes which are most near to each other. Okay, this is a very simple approach, a very beautiful approach in a way, to determine the positions of clusters. Now, the only problem here is this criterion I have told you only evaluates within cluster similarity. It doesn't say anything about the across cluster. In other words, if this is my cluster here, assuming this is one cluster, therefore this node, this node, this node is one cluster, the others are not cluster. I haven't told anything about the in between cluster A and cluster B, how these things are related. I haven't had anything in my optimization process across cluster differences are not considered. Therefore, it is a beautiful idea to maximize within cluster, but how about across cluster differences? Therefore, if you look at here, this is cluster A, this is cluster B. Within cluster, if we add them 2, 2, 5, 2, good, very high. This is large numbers, good again. But I have to also enforce that between across clusters, there will be very less similarity. There will be a normalization factor. This is the method called normalized cut. Okay, and the idea here is we are basically calculating the cut, the similarity between A to B. Cut AB means this 0.1 and that 0.1. You just simply normalize your cut divided by the volume of A, so that what you are saying is this. Let's minimize, previously it was maximization of this, but let's minimize this, taking two things into consideration. This similarity should be high, or similarity will be low across clusters. In the meantime, inside the clusters of A and B, let's have large values. Okay, therefore, we change our parameters in this way, and we cost function is basically rewritten, taking into account multiple things. Okay, these are some of the edges, volume of A and B, and our aim is basically construct an A and B automatically so that this thing is minimized. Let's mathematically formulate this, okay, using some algorithm. Now, first of all, if you take into the parentheses of cut A and B, you will obtain nothing but this one, okay, just 1 over volume A, 1 over volume B. Now, volume A, what is this volume A? Let's look at here. Volume A, the sums of 6, okay, we are having all the nodes, their sum of, if we have, this is called, for example, D1, this is called D2. We are having here nothing but this is equal to D6 plus D10 plus D11. Okay, therefore, we are talking about those diagonals. We simply add D6, D10, and D11, which is nothing but here, okay, only the indices of this A will be volume A. Similarly for volume B. Now, let's define an F different from this one. This is different from this one. Now, as you can see, I'm talking about, let's call 1 over volume A as alpha and 1 over volume B as minus volume B as beta. What I'm doing is this for this example. It will be beta, 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 when it's 6 alpha, 10 alpha, 11 alpha, okay? Therefore, in between beta, 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 it goes on like this. Now, I am filling my indicator function in this way. It's a new thing, okay? I am writing in a different way. Rather than 1, 0, it is like positive alphas and negative betas. Now, our Laplacian is still, as I have defined before, d minus w, okay? We are having like that. Let's multiply the Laplacian from left and right, with this f, okay? This f indicating of these things. It's multiplying everything from left and right, the Laplacian. And please note, the L is equal to d minus w. I can write it in this way. First I would like to show one little thing to you. This d and w obviously related to each other, as here. They are related to each other, okay? Therefore, for this term, it will be nothing but fi square, since diagonal. This is a diagonal matrix. Only the fi squares will be non-zero, I1 to n. You will have di's, okay? Therefore, I'm talking about like d1, d2, d16 multiply like beta, 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 alpha, beta, alpha, alpha, beta. It goes on like this, and one like that, beta, beta. It goes on like this. Now, please note, this is equal to nothing but, if you look at that, you will only have di squared, because as soon as you multiply this one, only the first term will exist. That term will be multiplied with this one. Therefore, this beta will be multiplied with this beta and with this d1. And this is nothing but matrix multiplication. We do a little trick here. We write it 2 times, di fi, and I write it from I1 to n and j1 to n, dj fj. And I obtain this term like here. This is somewhat interesting because fi square, there is a 1 over 2 here, minus 2. This 2 cancels to make it the single minus. I have fi square minus 2 fi fj and fj square. Hey, this is square, a complete square. Fi minus fj square here. But this is di, but this is wij. But note that wij is nothing but they are obtained just adding j1 to n di. Therefore, if you, this is a double summation, by the way. If you take one of the summations and if add everything, you will obtain again di. Hence, this Laplacian multiplication of from left and right with ft and f, in fact, nothing but our fi minus fj square from here, okay, multiply with wij, okay. We obtain nothing but this wij, fi minus fj, and that's an interesting result. Why? Fi is equal to fj if you are in the same cluster. If fi and fj in the A cluster, that's 0. If fi and fj in the second B cluster, again 0. When fi and fj are not in the same cluster, there will be non-zero, isn't it? Because we fill f using this technique. We have a constant alpha here, we have a constant beta here. Alpha minus beta is the only solution. And what we are having is this. This alpha, and these are only available, this summation, I1 to n and j1 to n, are only possible when you are here. Okay? When you are between two things like this one. Only for those cases, for example, these are not the case, you will not enter them. Only this one, this one, this one, this one, this one, and that one, and finally that one, you will have this one. I should belong to A, J should belong to B, one of them from one cluster, the other one for the other cluster, because otherwise that's 0. Only for those cases we have non-zero terms, and those non-zero terms are nothing but this one subtracted from here, since this is minus, nothing but the summation of these things. Hey, this is becoming similar to here, isn't it? Volume AB square wij, only we are adding all of these things. Let's go one more step. Please note ft multiply with a diagonal d from left and right, okay? We are having this thing. And since di is here, nothing but our diagonal entries, all my neighbors' similarity terms. Fi square is volume A, because this is only for volume A. Please note, otherwise all these things are I1 to n, okay? We will have just dividing this thing into 2 terms, like these are the alpha ones, these are the beta ones. Alpha ones and beta ones are divided to each other. The alpha ones are this, beta ones, there is a minus, but squaring it removes the minus. Therefore, I obtain nothing but like alpha squared di plus beta squared dj. Hey, this alpha squared di and beta squared dj is, what is that? This is simply, this is simply our terms only inside A and only inside B. Okay? Therefore, now what do we have here? This di. What is the result of di? Sum, this is constant, by the way, it can go out. I a to n di. Let's look at this one. If you sum I a to n, whatever, okay, just the di values, this is equal to nothing but volume A, okay? You just simply, all the entries 6, 10, 11 is written to here, and this is volume A. And volume A divided by volume A squared here will give you 1 over volume A and 1 over volume B. Good. Now what we obtain is this is equal to this one. And our normalized cut definition, that initial definition here becomes nothing but your Laplacian, graph Laplacian multiplied with left and right with f, which are defined in this way, divided by your diagonal degree matrix multiplied from left and right with the f. That becomes our thing to optimize, thing to minimize. Let's minimize this. Okay, this is the definition. Just a little note here. That term can be written in this form. Maybe it's in the first look how this could this constraint is equal to this constraint, how they are related. But please look at here. We have the D1, D16. If we have beta, if we have 1, 1, 1, 1, if we have these things here, that multiplication becomes a vector in this way, okay, which will be nothing but this one multiplied with D1 will be this, and there will be nothing but D16 okay, that will be nothing but, it was 16 by 16, it was 16 by 1, the result becomes 16 by 1, therefore nothing but all these things are written into a vector form. Now, if this is written into a vector form, if you multiply some of them with, beta, some of them with alpha, this D1 to D16, please note you will have all the terms with di, I is element of A, will be multiplied with alpha, and similarly the other ones will be multiplied dj, j is an element of B with beta. Okay, therefore please note there is a minus sign here. There is a minus sign here. Therefore that is equal to plus 1. That is equal to minus 1. That makes a beautiful 0 here. Okay, therefore this constraint, I'm not going to write it anymore. It will be nothing but this constraint. Minimize this with this constraint. The problem is finished. I converted everything into a mathematical form. Let's try to solve it. Just a little note, we have already derived this. Fi minus fj squared, positive here. Wij's are affinity is always positive. Hey, everything is positive. At least minimum 0. Therefore, this L is a positive self-definite matrix. The eigenvalues should be either positive or 0. Let's look how they look like. Solving this part is tricky. I don't want to have something in the denominator like this. I don't like this in the denominator. I would like to get rid of this. Since this is diagonal, I can have this as like d1 over 2, okay? I just try to obtain something like this, and I'm just writing this as a new thing as G, okay? This term will be G. I define this new G. Therefore, right now, the denominator becomes much simpler in terms of G. It will be G transpose G. Now, the numerator is a little bit tricky. Wherever I see an F, I have to write this thing, GD inverse. Therefore, from here, I obtain this thing, and my solution becomes, in other words, uh, instead of, I don't want to deal with these things anymore. I'm writing it like, instead of F, it will be D minus 1 over 2G, okay? Instead of this, I'm writing this one. And G transpose D minus 1 over 2 is the same. L is here, okay? Therefore, now I call this part, sorry, this part without the G, this is my L tilde. This L tilde is this guy, okay? Now it has a name, this time normalized graph Laplacian matrix. My minimum cut formulation is changing. It was initially this, perfect. Now this, but in the denominator, there is no more matrix here, just two vectors, a vector inner product with itself. Okay, this is a scalar. Please note this is a scalar here. The previous constraint, it was this constraint. On F, it was this. Please, wherever I see F, I'm gonna write this thing, and I'm gonna have this constraint. Now, I obtained the solution. I obtained the solution. Now, I'm gonna distribute some nodes indicating that the solution of this, is it is minimized by the minimum eigenvector, the eigenvector corresponding to the minimum eigenvalue of L tilde. I'm going to show you how it's obtained with some extra notes. Okay, therefore, this is obtained. This minimization is obtained by finding the eigenvector of this L tilde. Okay, good. But does this satisfy here? I mean, because this minimum eigenvector, does this satisfy the constraint? Note that, just a little note here, G is equal to D square root. This is diagonal. We can take the square root of this matrix, okay? Multiply with 1. Therefore, I'm talking about this. I can have this thing, okay? Now, what is this? What is this? I'm talking about here. Now, just write this. Instead of G, write it as L tilde D square root times 1, okay? Now, if you look at this term, you will have that L tilde can be written from here, this notation. Therefore, this thing is equal to this one. This D minus 1 over 2, D1 over 2 is identity. L times 1, one can easily show that. I really recommend you the eigenvalue. If you just multiply 1, that is exactly equal to 0, by the way. Therefore, that is equal to 0. Therefore, what I'm seeing is this. This is equal to 0. That's equal to 0. Therefore, D12, in other words, this square root of D multiplied with 1, which is a vector. This is equal to 1. Therefore, if the eigenvalue is equal to also 1, therefore, I'm talking about this, AX is lambda X. Now, if it is equal to 0, if this is equal to 0, any X making this equal to 0, therefore, it's a solution for eigenvalue is equal to 0 solution. And I showed that L, okay, L, our eigenanalysis multiply with this vector. This is the vector. This vector is satisfying equal to 0. Therefore, this is an eigenvector of this L tilde. Hey, this d square root of 1, d square root of 1 also satisfies the constraint. Therefore, what I'm saying is this. I obtain a solution, a minimum solution, where d121 is the solution of it, but the eigenvalue of it is equal to 0. Good. But here, please note, we will have nothing but constant entries, which is not very useful for us, okay? Therefore, this eigenvector corresponding to the 0 eigenvalue always exists since we are having a connected graph, and connected graph Laplacians, okay? Connected graph Laplacians are always equal to 0. Therefore, this is not something useful. For everything, for every connected graph, we have this one. I'm trying to minimize it. We are satisfying both of these things. Good. But starting from here, I came and just rewrite everything in this form, in the normalized Laplacian domain. But the above cut is satisfied by all the eigenvectors, and they are this one. Okay, beautiful. You can minimize it with this one. The ratio is as before. Please note, you will have as soon as you obtain an eigenvector, therefore eigenvector transpose L tilde eigenvector divided by eigenvector transpose E, that is equal to nothing but lambda times E transpose E divided by E transpose E. They cancel out, you obtain with lambda, okay? And we have the minimum lambda is equal to 0. It was, there is nothing larger than that one. Therefore, there is not smaller than that one. This is the minimum one, but it is always true for any connected graph. Therefore, these are the trivial solutions. We are looking for the second smallest eigenvalue, because always the smallest one, lambda is 0 for every connected graph. It is over there. Therefore, the second smallest will give you this thing to be minimum, but there is a problem. That second minimum does not satisfy this one. We need a relaxation here. The constraint is not satisfied. In other words, we say that, okay, let's use them. This is not satisfied perfectly. We use some little tricks to obtain a result. Therefore, we will simply threshold the components of this vector to have a result. In other words, we have a G. Unfortunately, nothing like this. This G is not completely satisfying this. The trick will be, this is the ideal solution maybe you are looking for, but this is the relaxed solution. The positive ones will be one cluster, the negative ones will be the other cluster. They will not be like this one, okay, perfect, alpha, beta type of thing. They will be somewhat relaxed solution, and such an affinity matrix of such a problem will give you, if you have 75 nodes here, these are the negative nodes, cluster A. These are until maybe 45. From 45 to 75, we have the positive ones. Those are the positive ones that we have here. Now, for image segmentation, we fill everything with intensity differences, okay? Everything will be filled by intensity differences. You can include your XY positions as well. You will just define another affinity matrix, but if you just simply do it by using intensity, it's also working. Let's look step by step. An image, m by n, like 100 by 200. The eigenvectors, everything is connected to each other. The affinity matrix will be 100 by 200 is equal to nothing but 20,000. 20,000 by 20,000 affinity matrix. The eigenvectors will be 20,000 by 1. Okay. And you will obtain, you will solve for the problem. The eigenvectors will be remapped. That was an image. 200 here, 100 here. This is the eigenvector. We remap from 1D vector to the 2D image once again. These are high positive values. These are low values. For a single row, just like this row, we are having this thing. These white ones are these guys. The small ones are these guys. You put a threshold and you say that you guys are one cluster, the other ones are the other cluster. Let me show you some results, real results. This is giving you, for example, one region, and this is just segmented. One region is here, another region is there, another region is here, another region is there, another one is there. And please note, the tiger with black and white stripes, completely contrast, different contrast. You are able to obtain it as a single object. Okay, you are obtaining it as a single object. Similarly, this staircase characteristic is obtained as a single object. And these are some other results from our famous Berkeley segmentation dataset obtained through this algorithm. Okay, now that was the concepts that we have learned for normalized cut. The algorithm was basically trying to obtain a G vector where the positive entries are showing one group of indices and negative entries are showing the other ones. We threshold them and we find the positions in that way. Now, the spectral clustering is a technique, and I'm gonna briefly explain it in the next video. Thank you.